3 in the morning. The phone on the nightstand reads 100%. It has read 100% for the last 4 hours. The charging cable is still plugged in. The little brick in the wall is still warm to the touch. The outlet is still feeding it electricity. So what exactly is happening in that cable right now? Why isn't the battery overcharging? Why doesn't it catch fire like the warning labels use to suggest it would? And how is it that one of the most volatile chemical reactions ever miniaturized into consumer electronics, a flammable lithium compound packed into a sealed envelope the size of a credit card, has been sitting next to a sleeping human face every night for more than 30 years without setting fire to the planet? The answer involves a Norwegian-born American chemist who never owned a phone, an entire digital conversation happening through your charging cable that you've never been part of, and a 100% that isn't actually 100%. Here's the first thing most people get wrong. They think the wall charger is the smart part of the system. The brick is doing the work, watching the battery, deciding when to stop. That's the mental model almost everyone has. It just happens to be wrong. The wall charger is, electrically speaking, kind of dumb. It's a power supply. It converts the 120 or 230 volts coming out of your wall into a low DC voltage your phone can handle. That's most of what it does. The actual brain of the operation isn't in the brick at all. It's inside your phone. There's a chip buried deep in the phone called the PMIC, the Power Management Integrated Circuit. It's about the size of a grain of rice. Its job is to monitor the battery voltage, the current flowing in, the temperature, the chemistry, and the state of charge all in real time, hundreds of times per second. Sitting next to it, often integrated into the battery pack itself, is a related circuit called the BMS, the Battery Management System. The PMIC and BMS together are the actual decision makers. They watch the battery the way a flight controller watches a jet engine. The wall charger is just providing fuel. This is why a fully charged phone left plugged into the wall doesn't keep filling with energy. The phone simply tells the charger to stop sending current. The charger obeys. The light stays on. The cable looks unchanged, but almost no electricity is actually flowing. The phone has politely closed the gate. Quick favor before we keep going. If you've ever wondered about the engineering hiding inside the everyday objects in your pocket, hit that subscribe button. We dig into the science behind the things you use without thinking. Now back to the charger. Here's the part that should genuinely surprise you. The phone and the charger aren't just exchanging electricity. They're having a digital conversation through the cable, in real time, while you sleep. Modern USB-C chargers use a protocol called USB Power Delivery. When you plug your phone into a USB-C charger, the very first thing that happens isn't current flowing. It's a handshake, a series of digital messages sent across a dedicated wire inside the cable called the configuration channel, or CC line. The charger introduces itself. It says, in effect, here are the voltages and currents I can offer. 5 volts at 3 amps, 9 volts at 3 amps, 15 volts at 3 amps, 20 volts at 5 amps. The phone reads that menu. Then it says back, I'll take 9 volts at 3 amps for now, please. The charger flips a switch internally, raises its output to 9 volts, and starts delivering. As the battery fills, the phone may even renegotiate, slow it down, drop the voltage, adjust the current. The conversation never stops as long as the cable is plugged in. That's why a high-wattage charger can charge a low-power device safely. The cable supports it. The phone asks for what it can handle, nothing more. Everyone agrees on the same number. Then the power flows. It's a digital protocol with handshakes, packets, and acknowledgements. A small computer talking to a smaller computer over a wire that looks, from the outside, like it carries nothing but voltage. Now for the actual charging mechanics. Lithium-ion batteries can't just be filled like a glass under a faucet. They need to be charged in stages. The first stage is called constant current. The PMIC tells the charger to deliver as much current as the cable and battery can safely accept, often somewhere between 1 and 3 amps. The battery fills quickly during this stage. Voltage rises steadily from around 3.0 volts up toward 4.2 volts. This is when your phone goes from 0 to roughly 80% in maybe 30 minutes on a fast charger. Then it shifts. Once the battery hits 4.2 volts, the system enters constant voltage mode. The voltage holds steady. The current starts dropping naturally as the battery saturates. This is the slow part. Going from 80% to 100% typically takes longer than going from 0 to 80, because the rate at which the battery can safely accept charge drops sharply at the top. When the current finally tapers down to around 1/10 of what it started at, the system declares the battery full. Charging stops. The PMIC closes the gate. Now here's the history almost nobody knows. The lithium-ion battery wasn't invented in a phone factory. It wasn't invented anywhere near a consumer product. It came out of a 50-year scientific journey that earned 3 men a Nobel Prize at ages 97, 77, and 71. It started with M. Stanley Whittingham, a chemist working at Exxon in the 1970s during the oil crisis. Exxon, of all places, was funding research into alternatives to gasoline. Whittingham figured out that lithium ions could be reversibly stored inside the layered structure of titanium disulfide. He had the concept. The early prototypes were unstable. They sometimes caught fire. Then, in 1980, at the University of Oxford, a chemist named John Goodenough proposed a far more stable cathode material, lithium cobalt oxide. It could hold more energy. It didn't burn as easily. The Oxford lab patented the work, but Oxford didn't see commercial value in it. The patent was eventually picked up by a small Japanese research company. In 1985, a chemist at Asahi Kasei in Japan named Akira Yoshino combined Goodenough's cathode with a new anode made from petroleum coke. The result was a stable, rechargeable battery you could safely manufacture and ship. In 1991, Sony commercialized that design and put it inside a camcorder. 3 years later, that exact battery chemistry started showing up in mobile phones. The same basic chemistry, refined and miniaturized, is in your pocket right now. In October 2019, Whittingham, Goodenough, and Yoshino were jointly awarded the Nobel Prize in Chemistry for the development of the lithium-ion battery. Goodenough was 97 years old when he won, the oldest Nobel laureate in history. And here's the part that should genuinely surprise you. When the Nobel Committee tried to reach him to deliver the news, they couldn't. Goodenough didn't own a mobile phone. The man whose invention powers more than 5 billion phones on Earth had never bothered to carry one of his own. Now for the surprise that almost nobody outside the battery industry talks about. Your phone never charges to 100%. Not really. The 100% your screen shows you is a manufacturer-set ceiling, deliberately placed below the battery's true chemical maximum. A lithium-ion cell can technically hold more charge if you push it to 4.35 or 4.4 volts. But the higher you push it, the faster it degrades. So phone makers cap charging at around 4.2 volts, sometimes lower in newer phones. That's typically about 90 to 95% of the cell's true chemical capacity. The other 5 to 10% is reserved as a safety margin. The same trick exists at the bottom. Your phone shuts off at 0%, but there's still real energy in the battery. The makers leave roughly 5% in reserve to prevent over-discharge, which damages the cell. So when you watch your battery go from 100 to 0, you're really watching it go from about 92 to about 5. The visible scale is a curated version of reality, designed to keep your battery alive long enough to outlast the phone. You've been participating in this same charging logic in dozens of places without realizing it. Your laptop, same negotiation, same constant current then constant voltage curve, larger battery, your tablet, your wireless earbuds, your smartwatch, all running the same chemistry, smaller cells, scaled down PMICs. Your electric car, just a much bigger version of the same system. Tesla, Rivian, Ford, every EV on the road uses lithium-ion in some form, with a battery management system that can monitor thousands of individual cells in real time. Your e-bike, your cordless drill, your robot vacuum, the drone you flew over the beach last summer, the pacemaker keeping someone's heart beating in a hospital nearby, lithium battery, charged once, designed to last 10 years, the James Webb Space Telescope, lithium-ion battery management at -200 degrees, charged from solar arrays, communicating with mission control. The Mars rover Perseverance, same chemistry, hardened for radiation. Every one of those systems is running some version of the same logic happening in the cable next to your bed, a small chip negotiating with a smaller chip about how fast to deliver electricity to a sealed envelope of lithium ions. Stop too early, the device dies. Stop too late, it burns. The PMIC has been balancing that knife edge for you, billions of times a day, since 1991. Now for the honest trade-off. Lithium-ion batteries do degrade. Every charge cycle wears them down a little. After roughly 500 to 1,000 full cycles, the battery's capacity will have dropped to around 80% of new. That's why your 2-year-old phone doesn't last as long as it used to. Heat is the worst enemy. Charging in a hot car, fast charging repeatedly, leaving the phone above 80% for hours every night. All of these speed up the chemical aging. Some manufacturers have started building in optimized charging features, where the phone learns your sleep schedule and pauses at 80% until just before your alarm, then tops off the last 20% right before you wake up. It's not magic. It's the PMIC and BMS using their full authority to slow the aging. There's also the wall charger waste. A typical phone charger left plugged in with no phone connected draws roughly 0.05 to 0.5 watts. Over a year, that's maybe 1 or 2 kilowatt hours, costing somewhere between 20 cents and $1. California has limited external power supplies to a maximum of 0.5 watts in standby since 2007, and most modern chargers are well below that. The vampire power problem is real but tiny. The thing actually wasting your electricity in standby is your TV, not your charger. So here's where you land. The brick in the wall isn't the brain. The cable isn't a passive wire. The phone isn't passively receiving electricity. What you're looking at when you charge your phone is an active digital negotiation, happening continuously between two small chips talking through a USB-C cable, managing a chemical reaction so volatile that a slightly larger version of it once grounded an entire fleet of Boeing 787s in 2013. They've been quietly handling that conversation billions of times a day for the past 30 years. While you slept, while you worked, while you forgot it was there. If you think phone charging is weirder than it looks, wait until we get into why your battery still dies after exactly 2 years, no matter how careful you've been with it. Because the thing that kills your battery isn't how you charge it. It's something the chemistry has been doing every single day since the moment the battery was sealed at the factory, whether you ever plugged it in or not.